Be easy with me. No proofing. Oops, oops. Come on. So how are you, everyone? Ethan, how come you were absent in the last class?
Good question. I had a computer science project that was due that day. I thought that it was due the same night as the homework. That would be lazy about it. And I would have, just didn't have time to come in.
Okay. Did you watch the recording?
Not yet. But I will tonight. I'm falling behind. I got lazy after my midterms. I put like catch up again. They are really.
You must.
Yes, I will.
Okay, while you were absent, we learned so many things. We learned about subspace, and then we learned about within the subspace, we talked about R2 space, R3 space, polynomial space, metric space. And then the last thing we learned about was null space.
That all sounds good.
Good. Who remembers what is a null space?
I'm sorry?
What is a null space?
Null space is a set with nothing. Oh, yeah.
No. I cannot blame you because you are not here.
Yeah.
See, it sounds like nothing in it. So there is a connection between nothingness and the actual set. So it is a null space. Nobody remembers anything? Emmanuel?
The space that has the solution.
Good job. Solution of what type of equations? Any type of system of equations, or there's a special type?
Vector. I mean,
System of equations, but what type?
linear.
Linear, good, and then another type, another condition or another requirement. It said it's a solution space for a set of all linear equations, but what type of linear equation? Say it again, I didn't hear you. No, we convert equation into matrix, but what type of equation? Not any type. See, now means nothing, right? So what type of equation? That has all the constant term is what? 0. So null space is a solution space. What type of solution is the solution of all homogeneous system of equations? Homogeneous means our right side of the equal sign, they all are 0. See, null means nothing, 0. So right side of the equations, they all have 0, 0, 0. So it's a solution space for homogeneous system of equations. Now, do you at least remember how do you find the null space?
The first step is turning everything to row echelon form.
Good job. Thank you, Elsa. At least you remember something. My other section is much better than you guys. Surprisingly, I expect actually more here. Huh?
Your grades too.
Exactly. They have
Yeah, you can do earlier.
over 100. Yeah, that could be one reason too.
Our grades are good. Our grades are great.
Compared to them, no.
Yeah.
They have almost 12 of them above 90 or 100.
Wow.
I was like, who? I think only who? Let's see. Mehrab and you. No, Mehrab, you and Abid. 3. Mehrab, he's absent. He sits in front of you, a little bit in front. It was before skipping class. Now I am wondering about the second exam. Now you guys are getting absent. So I wonder. I actually graded the first exam kind of with sympathy and kindness because I was absent a lot. Remember the online classes was something. No, it was after exam. Oh yeah, even though it was after exam, but I didn't grade the exam until I was absent. So I was lenient. Now I do. That way people are getting absent. I was like, I'm going to grade the second exam harshly so that you can see how hard the final exam will be. Not only you guys, like attendance for my other class is really bad. Compared to my other class, you guys are doing great attendance wise. You guys are at least here, but they are not here. So I'm going to grade, actually I should warn them. I'm going to grade their exam very harshly. Exactly. And I have my attendance list, so I know who is here and who isn't here. It's a good thing. It's kind of a threat. Yeah. But you're absent only once.
Yeah.
So far, whatever or however many days I took the attendance. So yeah, I'm happy actually attendance wise. I'm happy for you guys. Thank you for being here. Thank you. But learning the material, they are learning more than you guys. Why is that? I'm teaching the same stuff, explaining same thing, but why? One thing I noticed, they actually do the homework with all the steps. You guys give me only answers. Exactly. I think that's the main reason.
I only did it one time.
Not everyone. You shoulder step. Not only you, like there are few of you shoulder steps. By these guys in the middle. See? They think I'm dumb. I don't know what is AI. Okay, null space. So we know to find the null space, we have to reduce our matrix into rational form, or at least reduce rational form. So let's do one example before we go to the next concept. We are happy with 1. We are not happy with 2. So our goal is to make these 2 into 0. What do you do? How do you get a new row 2? 2 row 1. So if you do 2 row 1, we get 2 times 2, 2 times 2, 2 times 2, 0. And if you subtract all of them, change their sign. So we keep our row 1, which is 1, 1, 1, 0. And when you subtract 2 minus 2, 0, 1 minus 2, negative 1, 0 minus 2, negative 2, 1 minus 0, 1. And then let's make this one into 0.
Row 1 plus row 2.
New row 1 is row 1 plus row 2. So 1 plus 0 is 1. 1 minus 1 is 0. 1 minus 2 is negative 1. Man, it doesn't work. Sometimes it happens. I don't know why. Let me save it. Save. Pencil works, but Word doesn't save it. It happened in my my other computer also.
That's a nice one.
Thank you. Yeah. Okay, does it work now? So we have 1 plus 0 is 1. 1 minus 1 is 0. 1 minus 2 is negative 1. And then 0 plus 1 is 1. And let's also divide or multiply this one by negative 1. Divide or multiply doesn't matter. Yes, row 2.
Oh, yeah.
So we have 0, 1, 2, negative 1. How many variables do we have?
2. 4.
4 variables. This is x1, this is x2, this is x3, this is x4. In a system of homogeneous, homogeneous system equations, they do not use augment matrix because the last row, the last column is all zeros. So they ignore the last column and they use only the coefficient matrix. So this is a coefficient matrix we are reducing. So what information we get from here? X1 plus, not plus, minus. X1 minus X3, and then plus X4 equals 0. And the second line is telling us
X2,
X2, 2X3 minus X4 equals 0. Now, from the first line, if you try to solve for X1, what is X1? X3 minus X4. And if you solve for X2, what is X2?
negative X2.
Negative 2X3
Uh,
plus X4. Then what is X3? X3 is X3, it's free. What is X4? X4 is X4, it's free. So X1 and X2, they are not free, they are dependent, but X3 and X4,
X3.
because X1 and X2, they both depend on X3 and X4. But X3 doesn't depend on anything. But X4 doesn't depend on anything.
Yeah.
Now we are going to write our dissolution in a matrix format.
The three variables are just equal to themselves.
Yes. So X1, X2, X3, X4. So X1, X2, X3, X4. Let's write them down in a matrix format. X1 is negative 2X3. Oh, not here. Negative 2X3, positive 1X4. Right? Now X2 is negative 2X3. Wait. I'm doing the other one. X1 is 1 and negative 1. X1 is 1X3 and negative 1X4. X2 is negative 2X3, positive 1X4. Right? X3 is X3 and X4 is X4. So all the missing pieces, what do you do? 0. So 0, 0, 0, 0, 0, 0, 0, 0. This is 0, this is 0. Now this entire column is 0. This entire column is 0. Every column that has full of zeros, disregard them. They're useless. We have two columns that contains non-zero elements. This one and this one. So these are the two solution vectors we have. They lie inside our null space. So we write null space of A. We indicate that by n of A or null of A. And we write this as a span of these two vectors. 1, negative 2, 1, 0, comma, negative 1, 1, 0, 1. It means our set of solution, it's a combination of these two original solution sets. Span means all the rest of the other things, there would be a linear combination of these two. But the main solution are these. So that tells us our dimension of the null space. Dimension of null space. We represent that with the word nullity. And how do we find the dimension of the null space? Who remembers? 2, how do you know? 2 vectors. So null space is a span of the solution sets and how many solutions that you have or how many vectors you have. That's the dimension of the null space.
My entire guy is kind of lost how you build it in that table of X1.
X1 is 1, X3, negative 1, X4.
Right.
So X1 is 1, X3, negative 1, X4. Now X2 is negative 2, X3, positive 1, X4. So X2 is negative 2, X3, and positive 1, X4.
Oh, okay. Yeah.
X3 is itself. So X3 is X3.
And not x4.
No.
Cool.
And x4
Is
is
it-
x4.
Cool, thank you.
Everything else, 0.
Thank you.
And we have to write this down. Why? Because we need the vectors, non-zero vectors.
Use them for other things besides the.
We need them to know what is our null space. Null space consists of which vectors? They consist of these two vectors. It means these are the solution set for this system of homogeneous linear
Why do
equations.
we have to draw them in the first place? Why could, I mean, I guess to
How can you?
define what the vectors are,
Mhm. So you need to write the vectors form, the solution in vectors form.
you can't, so you can't say that the null space is the span of x2 and x3.
No. It's the
Or
vectors.
x3 and x4, and then.
So it's x3 times that, x4 times that. So x3 of this plus x4 of this. We don't have to add x3, x4, because if you write the vector, we automatically know.
Yeah.
Okay. So that's the last thing we learned in our last class. And now you're going to enjoy something.
Yep.
2 videos about what we are going to learn today. So let's watch our videos and have fun. Did you guys go to elementary or middle school in this country?
Yeah.
No. I went to middle school. They used to let us watch cartoons, movies, everything. I was like, I just came from my country and my country was really strict. And I was like, wow, what type of school is this? Like, they let us watch videos, have fun. Like, wow. I was really
Was
amazed.
it Bill Nye or
Hmm?
Bill Nye the science guy?
No, I went to Michigan.
Bill Nye.
Bell Nye, what is Bell Nye? I don't know actually what is Bell Nye. Fine.
Science guy, Bill Nye.
You know, they used to watch us movies. Like, I remember one movie they showed us, Don't Go Downstairs. There was a movie around that time. Don't go to downstairs. And it was a scary movie, spooky movie. I remember that movie. And once they watched some Indian movie, he was like, wow, really? This country, education is fun in this country. In our country, they used to beat us up. Bangladesh. They have a stick, and if you don't do anything, that's how we learned. How we learned, you guys are like bathing everything. Okay, enjoy.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between.
Rewind. Okay. Linear combination is on the bottom. Linear combination span and basis vector by 3 blue, 1 brown. What does that mean?
This first quote is absurd.
In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are 2 very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3, and the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of 2 scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale.
Origin, no
There's
fun.
also a more technical definition, but I'll get to that later.
Jackson, no
By framing our
computer,
coordinate system in
please.
terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system. For example, take some vector pointing up and to the right, along with some other
Emmanuel, no
vector
fun,
pointing down and to the
please.
right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe
The vector always has to be like.
Starting from origin.
Like, whenever like, always.
There is one vector has to be at the origin, and the other vectors, if you add them or subtract them, it has to be from the tip of the first vector. For example, here we have x vector here, y vector here. So this y vector is at the tip, it starts from the tip of the x vector. So whatever position you are in, you have to draw a vector from the origin to that space, that place, that position.
vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors. Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors.
Can you pause here?
So span means how much you cover from two vectors. So if you have two linearly independent vectors, means they have no connection with one another. And if you add them by multiplying some constants, then you can cover the entire space. So the first vector was here, the second vector was in. So this was first vector and this was third vector. So second vector. If you add the first vector to the second vector, the result comes here. So from origin to here, if you move around your constant, like whatever you're multiplying by, then that tip, the result will be everywhere in your xy plane. So this is the span, how much it covers from your space or within your space.
The Pythagorean theorem again.
Yes, if you have two independent vectors. But if you have the same vectors, just a multiple of one another, then you cannot use Pythagorean.
So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space. But when they line up, their span is all vectors whose tip sit on a certain
If
line.
you have two dependent vectors.
Remember how I said that linear
Then
algebra
just
revolves
line.
around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar
So
multiplication.
how much you can cover
This
by
is a
the
good time to
combination
talk
of
about
two
how
lines
people
in
commonly
your
think about
space.
vectors
That's the
as
span.
points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling up the plane. So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line. The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors you get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the linear combination, adding the scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors. Or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image? So what happens if we add a third vector and consider the span of all three of those guys? A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations.
The order matters here.
We always go to first X, Y, and then Z. Actually, it does matter.
Order does matter.
In 3D, we have to go X, Y, X first, then Y, and then Z.
Two different things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand,
Well, lower before. Perfect. Thank you.
So basically, so far what they're saying is that if you have only one independent vector and the rest are dependent, like the other vectors are multiples of the first vector, then the only thing you can cover in your space is a line. with only one vector, one independent vector, it gives or it covers only one line. But if you have two vectors, two independent vectors, it covers a plane, an XY plane. And if you have a third vector that is a dependent or a linear combination of the other two, then still it doesn't change your span. It doesn't change how much you're covering. If you have two independent and the third one is a dependent, you're still covering just a sheet, a plane, okay? And if you have three independent vectors in R3, then you're covering the entire 3D space. This is what they have.
On the other hand, if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense.
So basis means the collection of all linearly independent vectors that span the entire space. And now there is another video. Oh, are you writing something, Andy? Okay. So we learned linearly independent. It means one vector cannot be expressed in terms of other vectors. Span means how much you're covering with your vectors. And basis is how many independent vectors you have. If you have two independent vectors in R2, then it's a basis which covers the entire space. So if you have linearly independent vectors that cover the entire space, then those vectors are basis. Guys, no phone, please. I'm making you watch this because I'm success explaining all these things. Okay.
This includes understanding what it means for a set of vectors to be linear independent. Today, we explore some of the basics of linear algebra. This includes understanding what it means for a set of vectors to be linear independent, to span, or to form a basis
now,
within a
mathematically,
field.
how do we understand
We consider
all
the
of this?
set of vectors v1 through to vm in a field Rn. This means column vectors with n entries. We first consider the linear combination of our vectors v1 through to vm. This means we have a constant before every vector before they're added together, i.e. x1 through to xm are all constants. Now, say this linear combination equaled the zero vector, and let's say this is only the case if all of our constants equal 0. Well, this is what it means for v1 through to vm to be linear independent in Rn.
So what does that mean? They're saying if you have a bunch of system of homogeneous linear equations, and if you solve them, if every variable equals to 0, then they are linearly independent. Okay? For example, if you have 2x plus 3y equals 0, and then 4x plus 5y equals 0, if you solve them and if you find out that x1 is 0 and also x2 is 0, that means the two vectors we have here, they are linearly independent.
So let's look at an example. Say we have three vectors in R3 and we want to know if these are linearly independent. Well, let's say v1 equals 3, 2, 2, v2 equals 5, 3, 2, and v3 equals 4, 1, minus 5. So the question we're asking is if we put this into a linear combination equaling the zero vector, is it necessarily the case that x1, x2 and x3 equal 0? Well, we can convert this linear combination into a matrix form, to which we can conduct Gaussian elimination to find out what these constants need to be. If you haven't already, I recommend watching my video on Gaussian elimination so you understand what's going on here. I will link it in the description below. So returning back to our matrix, we want to convert this into reduced echelon form. We start by subtracting row 2 from row 1, then we subtract 2 times row 1 from row 2 and 2 times row 1 from row 3. Then we times row 2 by minus 1. Then Finally, adding 2 times row 2 to row 3 and timesing by -1. And there we have it. We've converted our matrix into reduced echelon form. So putting this back into the system of equations and equating our coefficients, we see that x3 has to equal 0, which implies that x2 equals 0, and finally x1 equals 0. So we have that these three vectors in R3 are linearly independent.
You see, if you solve them using row echelon form or reduced echelon form, you find out that all three variables x1, x2, x3, they are 0. That means the three coefficients vector you have, they are linearly independent. It means one of them you cannot express is a linear combination with other two.
Let's return back to looking at
don't have a free variable. It's linear. What do you do?
No, if you have all variables have a unique solution, and this unique solution here is 0.
Yeah, and our
So the example we did before, we did not have linearly independent solutions, linearly independent
Yes.
vectors.
we had free variables.
Exactly.
our general sequence of
Infinite
vectors
solution or no
v1
solution,
through vm
they are not
in
independent.
Rn. Let's now say that our linear combination of our vectors equals some arbitrary element b in Rn. If it's the case that there always exists an x1 through xm in the real numbers such that this statement holds, we say that v1 through vm span Rn. So now, how do we test this? Well, if we bring back our example before, but the reduced echelon form matrix, if it's the case that there's no rows full of zeros, we can say that it spans. But here, changing that one element means that this set of vectors would not span R3. Let's move on to the last definition of this video, looking at bases in Rn. So, if we have v1 through vm, we say it's a basis if v1 through vm spans Rn and v1 through vm are linearly independent in Rn. The most trivial basis of Rn is called the standard basis. Here, we have that the ith element of the ith vector equals 1 and the rest of the elements are 0. To conclude this video, let's contemplate the main theorem for Rn. This brings together all the topics we have covered thus far. The first part of this theorem is that every basis in Rn has n elements. So let's consider m vectors in Rn. Let's say that this forms a basis. So we put this into matrix form and convert it into reduced echelon form. To span Rn, it must have a leading entry in every column, and to be linearly independent in Rn, it must have a leading entry in each row. Therefore, we have that m must equal n, and that every basis must have n elements. We move on to the second part of this theorem, which follows from what we just said. We have that these following statements are all equivalent. For a set of vectors v1 through to vn in Rn, if these form a basis, then they also span Rn, and they are also linearly independent in Rn. Throughout this video, we've only contemplated results in the real numbers, but this also generalises into complex numbers and any other field. So I hope you've learned something new from this video or consolidated some old knowledge.
Okay, so now you know what is linear combination, what is span, what is spanning set, what is linearly independent, all these things. Now, two examples of linearly independent and not linearly independent is here. The first one, we have 1, 2, 3, first vector, 4, 8, 12, second vector, and then 8, 16, 24, the third vector. Are they linearly independent?
Yeah.
Of course not.
You should. Oh, you did. Oh, I thought
The
that.
second column, the second vector, then this, the second vector is 4 times the first one. The third vector is 8 times the first one. So these two are dependent on this one. So the set of 3 vectors here we have, they are not linearly independent.
What? Say that again?
If you multiply this vector by something, can you get this one?
Yeah.
If you multiply this by something, can you get this one?
Isn't it for vectors? Isn't the dependence from the verticality, so it's up from up to down.
No, dependence comes from linear combination. If you can multiply, if you can get one vector by multiplying another vector or by a linear combination of other vectors, then they are not linearly independent. Like the first three sets, they're not linearly
In
independent.
the video, did he take these three matrices and merge them into one? And then solve it? To reduce it? I mean, and he did.
We did that because we didn't know, but here we clearly see these two are not independent. They
Because
depend
of
on this.
visibility.
We can see that these two are multiples of the first vector. So when you see clearly, you don't have to do a reduced echelon form. When you don't see clearly, like this one, I mean, this one is also clear. 1, 0, 0, 0, 1, 0, 0, 0, 1.
And that.
They are
that
not.
Visibility needs to carry across all three vectors.
What, Katie?
12 needs to be divisible by 3 and 24 needs to be divisible by 3 in order, and for every row as well, like we have to look through to make sure that
All of them have to be multiples
for
of.
every row and every matrix.
But if you have second set, 1, 0, 0, 0, 1, 0, 0, 0, 1, then they are linearly independent. How do you know? There is no way you can get this vector by multiplying this one with something. It's not possible. Or you cannot get this vector by multiplying this one or that one, or even by adding them. So three vectors, they're completely unconnected or unrelated to one another. So they are linearly independent. Now, depending on which space you have, if you're in R2 space, you're allowed to have only 2 maximum linearly independent vectors. If you're in R3 space, you can have maximum 3 linearly independent vectors. So the dimension of the vector, dimension of your space, is the maximum number of linearly independent vectors that can be contained in that space. Okay? So if you have 4 vectors in R3, the fourth vector or one of these vectors has to be a linear combination of the other 3. Now for bases, we already know there are 2 conditions. All the vectors we have in a set, they have to be linearly independent and they have to span the entire set. What does that mean? We're going to do a few examples later. But for now, what are the bases? If you're in R2, there are 2 standard bases, 1, 0, 0, 1. It means our x value is 1 and our y value is 1. So 1, 1 is a standard basis. If you're in R3, we have 3 standard bases. 1, 0, 0 means the x value, 0, 1, 0 means the y value, and 0, 0, 1 is the z value. So these are the standard bases, means they are already there. If you have them, it's automatically, you should know that they are bases for R2 and R3. And there are also some other vectors, which we don't know just by looking at them, but these are some examples of bases. These 2 are 2 sets of bases for R3. 1, 1, 1, 0, 1, 1, 2, 0, 1. How do you know? You can find somehow that they are not linearly independent. And if you have 3, so they are linearly independent. If you have 3 linearly independent vectors in R3, then they span the entire set. And if they span the entire set and also the linearly independent, then they are bases for your space. Now for bases, for the dimension of your space, you have to have exactly that many vectors to be bases. For example, in R2, you can have exactly 2 bases. You cannot have 1 basis or 3 bases. Exactly 2 bases we have in R2. In R3, there are exactly 3 bases. We cannot have 4 bases or 2 bases or 1 basis. We have to have exactly 3. If you don't have 3, that means they are not bases.
Professor, did you publish these slides or just recording?
Just recording.
Do you mind publishing these slides?
Okay, I'll upload them on Brightspace. Once you're done with this, I'm going to upload them.
This is complicated. Like, yeah, I don't want to take this computer.
No problem. Now, when you go with linear combination, what type of operations are allowed in linear combination? You can say one vector is a linear combination of other vector, or one vector is the same thing, like x3 equals x3, remember we did before? So it's a combination of other vectors because we have 0x1, 0x2, 0x4, remember? So x3, even if you have only one variable, it's a linear combination of other variables. Or you can have visible numbers like 3x1, half x2, 10x3. Those x1, x2, x3 here they are represented by vector v1, v2, v3. So you can add them with a constant multiplication, or you can subtract them. These are allowed operation. Then what is not allowed? Multiplication of the vectors. You can multiply a vector by a constant, but you cannot multiply two vectors. Or you cannot take the square of a vector. Or you cannot add a constant. You can add the vectors, constant, multiply. You can multiply by a constant and add the vectors, but you cannot simply add a scalar, add a constant. You can multiply by a constant, but you cannot add them. You can add two vectors, but you cannot multiply them. Blah, 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 blah. Now, the thing we said, we watched in the recording, they are saying that if you have one vector, then what happens? So if you have only one vector in your space, it doesn't matter which space you are in, either R1, R2, or R3, they span only, they cover only a line. So their span is only a line, nothing more than that.
Talking about what creates a line.
For example, here, let's see the vector 1, 1.
Yeah, I see it.
Now you have one independent vector. The rest vectors are dependent on that vector. So if you multiply by 2, you get 2, 2. If you multiply by 3, you get 3, 3. If you multiply by -1, you get -1, -1. So if you place all these vectors in your plane, you're going to see them, all of them, they're going to give you only a line.
Why equals X.
Y equals X. So the span of one vector in your space is just a line. And I'm going to ask this in the exam. What is the span of one independent vector? It's a line, not all real numbers. So one vector, let's say this vector. If you have a multiples of this vector, either you're making it bigger, or you're making it shorter, or you're subtracting here. So it doesn't matter what you do, they will always create just a line. So their span means how much they cover. It's just a line. But there's a different story when you have two independent vectors in R2. Sorry, two vectors in R2. So if you have two vectors, depending on what type of vectors you have two scenarios. If you have two dependent vector, for example, one is 1, 2,
Yeah.
and the other one is 6, 6. Clearly, they are not independent.
Yeah.
How do you know?
V2 is 3 or V1.
3 times V1 when I give you V3, V2. So they are not independent. So if you try to, it doesn't matter what type of linear combination you have, you can take so many types of linear combination. So for example, you're going to get 4, 8 if you add them. You're going to get -1, -2 if you do 2V1 minus V3, you're going to get that. So it doesn't matter what combination you do, look at the end result. If you try to plot them on your plane, you will see that they're creating just a line. So what's the bottom line? If you have only one independent variable, it doesn't matter whether you have many dependent variable or not. The result is same. It spans only a line. But the story is different if you have two independent variable. Not variable. Two independent vectors. Let's say we have one vector on the x-axis 0, 1. Sorry, 1, 0. This one should be 1, 0. Right? Our x value is 0, y value is 1.
Yeah, you got it mixed up.
Yeah.
So,
The picture should be
Yeah.
rearranged. So we have two vectors, 1, 0, 0, 1. And if you try to add them and then multiply them with a constant and then add them again, So if you do 2 times their sum, it goes here. If you do 3 times one of them plus the other one, it goes a little bit tilted toward x-axis. If you subtract them, it goes downward. If you do 1 minus twice other one, it goes in the 4th quadrant. So if you keep doing all sets of combination, observe what is happening. You point here, 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 here. So you're covering
That plane that I forgot.
the entire plane.
What was it
uh,
called?
XY plane.
The basis?
Yes, so these two are the bases because they cover the entire plane, the entire space. We are in R2 space, and what is R2 space? It's a plane, XY plane. So you have 2 vectors, they're linearly independent, and they span the entire space, means they cover the entire space. So they are bases. So if you have 2 dependent, they do not span the entire space, so they are not bases. But if you have 2 independent in R2, 2 independent vector in R2, they span the entire plane, so they are bases in R2. So I'm going to ask, what's the span of 2 independent vectors? They're going to say it's the entire plane, entire R2 plane, XY. And now let's do some example. Oh, before that. So when you're in R2, life is easy because we can see clearly whether 2 vectors are independent or not. How do you know? We can see that if one vector is constant as another vector, then they are not independent. And if they're not independent, then they do not span the entire plane. But let's say you're in R3 space, or R4 space, or R5 space. They need to be hard to figure out whether all the vectors you have, they're independent or not. So that time, one of the easier methods is to look at the determinant. If you write all those vectors in a matrix form and take the determinant of that matrix, if the determinant is not 0, that means you have unique solution.
But didn't you
Yeah.
do determinant or Gaussian elimination?
So if you have 5 by 5, I mean, if you have 4 by 4, if you have 3 by 3, whatever, either Gaussian elimination or determinant, one of them. But for 3 by 3, determinant is easier.
But so you're taking the determinant of one matrix in the set?
No,
Oh,
you are writing down all those vectors in a matrix form, and then you're taking the determinant of that matrix. If the determinant is not 0, then they are independent, it means they're good. And if you have 3 independent vectors in R3, that means they're going to span your entire plane. So they form a basis. Now the fun part, we have 15 minutes, yay. Let's do some example. We have 2 vectors, 2, 1, and 3, 2 in R2. And they're saying determine whether these 2 spanning set for R2 means do they span R2? So you have to span R2. What do you have to look for? Whether they're independent or not. So we need to see, are they independent? Or we should say linearly independent. So i.e., are they linearly independent? So you have 2 methods. Either you look at the determinant. So let's see the determinant. So you write down the matrix 2, 1, 3, 2. I mean, what's the determinant of that? So let's say A is 2, 1, 3, 2. What's the determinant of that? 2 times 2, 4, minus 3 times 1, 3, which is 1. And this is not 0. If they are not 0, they are good. They are independent. So this one is easy because it's in R2. So you're looking at the second step. Can you multiply, can you multiply 2, 1 by something so that it turns into 3, 2? Is it possible?
No.
In order to get from 1 to 2, you need to multiply 1 by 2. So if you want to make 1 into 2, you need to multiply with 2. And if you multiply with 2 on 2, you should get 4. I don't have 4. So it's not possible. Since it's not possible, so they're independent. So these two are linearly independent. So we have two linearly independent vector in R2. So they are spanning sets. So we have two linearly independent who span the entire set. So are they bases or not a basis?
How many sections are we covering for sensitivity?
This is 3.2. So we are going to see.
Where did we stop the fourth test?
Our exam is after 2 weeks.
No,
So-
what subchapter did we?
No, like what chapter?
Chapter 3, I think.
Student starts on chapter 13?
No, it starts on 1.5 or something. 1.5 or 1.6, something like 1.5. The LE factorization. That
1.5, chapter 3.
1.5, chapter section 2.1, 2.2, and then chapter 3. Determinant and inverse. I'm going to make a review sheet, so you'll see. Okay. NG, so is it a basis or not?
That's a bit.
Good. So they are basis.
How did you find out their spinning set? Like, you just compare them.
If you have two linearly independent set in R2, then do they span the entire set? Yes. That's how you know they're spanning set or not.
So it depends on the dependent variables.
Independent. How many independent variable you have? In which dimension?
3 variables.
Oh.
Independent means you cannot write one of them in terms of other one.
Okay.
They're independent. They have no connection, no relation. Kenyan, what question you had?
What do you mean by base?
The characteristic for basis is two things. They have to be linearly independent and they have to cover the entire space. Spanning means covering the entire space. So we have two vectors. First, we checked whether they're independent or not. So we found, yes, they are linearly independent.
Okay.
And then we look at which space we are in. We are in R2 space with two linearly independent. If you have if you're in the R2 space with two independent vectors, that means they're going to cover your entire plane.
Yeah.
So it's a spanning set and they are independent. So they're basis.
Well, that's the condition for making that base, but what you mean by base?
Basis is a set of collection of all the linear combination of collection of sets that contains all linear combination of what they call them. Here. Base. Come on, I don't have it here. So it's a collection of set that contains all linear combination of your linearly independent vectors.
What?
Basically, you're asking what is your base?
What is
Okay.
your base?
It's kind of like that. Like if you build a building, first you need to create your base, right? So why the bases are important? Because they build the entire building. Same thing here. If you have two strong original base in your matrix, in your space, that means the rest is fine. The rest is strong because you have your two strong bases. You asked me why it matters, right? It matters because they are the foundation. They're the foundation of your entire space. So they're good. So if you have a set of vectors, then that basis, they are not good because they don't create or they don't have a good foundation for your metric space. Not elementary. Elementary metrics are independent are bases. See, elementary metrics, no, elementary metrics. Identity metrics are bases, not elementary metrics. I don't know. Elementary metrics are they? Do they have determinant 0? Check. If they are determinant 0, then they are not bases because they are not independent. Why not? So this is V1 and this is V2. Our V2 is twice V1. So one vector is a dependent vector of the other one. So one vector is a multiple of the other vector. So they cannot be a spanning set. They cannot span the entire space. So what's the spanning set for them?
I have a question. It's like, if one is like a multiple of the other, then it's like, it should be like two, like it should be like, two different like sets, but since one is a multiple, it's really just one set.
Only one vector. And if you have only one independent vector, how much they cover in your plan? The line. So the spanning set for this one is a line, not the entire space. But the question is asking, do they span entire space? That's what the answer is no. They do not span the entire space. They span only a line. So I should write. They span only a line, not the entire plane. Okay, next one. -1, 2, 1, -2, 2, -4. Are they a spanning set for, is this a spanning set for R2? Why not?
Yes, it is.
So what's the condition to span the entire space? Independence. Linearly independent. Are they linearly independent? No. First of all, you have 3 vectors in 2 space. Definitely one of them is not independent. So you cancel out whatever is you want to. And then you look at the other 2. The 2 remaining one, are they independent or are they dependent? They are dependent, they are not independent. Because the first one, if it's V1 and the second one is V2, we know V2 is -1 V1.
This is R2, then like each vector only has two numbers.
Number of rows.
Number of rows.
So Rn, that n is number of rows.
1 by
N by 1.
n by
N rows, 1 column.
And then if it's like if it's R3, then you're expecting to have like 2 columns.
Not 2, 3. So R2 means you have this and that. R3, it means there are 1, 2, 3 lines. The vector, number of vectors. In order to span, you have to span the entire R3 space, you need 3 independent vectors. For example, the next one. We have 3 sets of vectors. Which space is it? R2 or R3? R3, because we have 1 row, 2 row, 3 row. 3 row means R3. Why not independent? So see, for 3, it's hard to see. That's why you have to use the determinant.
Oh, we're doing addition, it's addition, yeah.
For 2 vectors, it's easy to see. But for 3 vectors, it's hard to see. So 1, 0, 0, 0, 1, 1, 1, 0, 1. I like this method. So 1, 0, 0, 0, 1, 1.
You're taking 4 minutes.
So determinant, let's see. This is 1, this is 0, this is 0. and you're subtracting, huh? That's how we find determinant. You take the right diagonal and you subtract the left diagonal. So left diagonal, the first one is 0. The second one is also 0. The third one is also 0. So what's the determinant?
This.
Huh? This one is easy method. I love it because once you rewrite, see, everything is easy, just multiplying. So determinant is not 0. Since determinant is not 0, are they linearly independent or not? Determinant not 0 means a good thing. So they are linearly independent. Now, why do we care? We have 3 linearly independent vectors in R3 space. Do they span the entire space? Yes. They span entire R3. Now the third question. You have 3 linearly independent vectors in R3 which span the entire space. So are they bases for R3?
Yes. I think there are.
Good job. So they are bases. Means they are foundation of your R3 space. One of the many foundations of your R3 space. Last question before you go. Same question. Do they span R3?
Yeah, I think so. Yeah.
Question number 1. Are they linearly independent? Are they Are they linearly independent?
I definitely see it because like they have more than 2 independent variables, so they're literally independent.
No.
But you have 4 vectors in R3.
Yeah.
Not possible, man.
Right. We have 4 vectors in R3. Remember, the dimension tells you how many independent vectors you're allowed to have. In R3, how many vectors you're allowed to have the linearly independent? 3. So you have 4 of them. Are all 4 linearly independent? Definitely not. One of them must be dependent. So can you choose which one? Can you see which one?
That's the fourth one.
Fourth one? If you can see, it cancel out, and then you look at the remaining 3. Now the remaining 3, are they independent or they are not independent?
No, they're not.
So you have to check. You have to look at the determinants. 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1. And then you find the determinant exactly same way I did the last one. You add all of these and you subtract all the left ones, 0. So determinant is not 0. That means we have 3 linearly independent vectors in R3. So do they span R3? 3 linearly independent vectors in R3. Do they span entire R3? Yes, even though we have a 4th one, but it doesn't change our spanning scenario. So they span R3. So they span R3. Question.
Yeah. So, like, you could cancel it out because it should be a multiple of the other one.
It's definitely a multiple of the other one. Oh, actually, there's an interesting one. If you don't cancel out this one, but you cancel out any other one, look what happens. Give me 2 minutes, 2 minutes, 2 minutes. Give me 1 minute, okay? 1 minute. The interesting thing here, if you do not cancel the last one, what happens? We have 1, 0, 0, 1, 0, 1, 1, 2, 3. So 1, 0, 0, 1, 0, 1. Look what's the determinant we get. This is 0, this is 0, this is also 0. Now subtracting, this is 0, this is 2, and this is 0. Or this works. The first one didn't work. Let me show you 1 minute, okay. 0, 1, 1, 1, 0, 1, 1, 2, 3, 0, 1, 1, 1, 0, 1. So if you look at these two, these three actually, this is 0. Oh, no, what I'm doing, the right one first.
Oh, what?
This is 0, this is 2, this is 1. So 2 plus 1, and you're subtracting, this is 0, but this is 1. So what do you get? 3 minus 3 is 0. So just because you have determinant 0 doesn't mean they are not independent. You have to check all these combinations. If one of the combination gives you determinant 0, that means they are linearly independent. But it takes time. If you don't want to waste your time during exam, your hope is to convert this into row echelon form and then see what's the value you get. If all the values are, you have unique solution, then it's independent. Otherwise, it's dependent. Okay?
Thank you.
So remember, you have a homework due tonight, and also there is a homework on this section, 3.2, which I'm not going to assign next week, but you can start doing them. So have a good weekend, everyone.
Do you have access, did you give us access to the textbook? Or, cause I saw a link, but,
Really?
yeah, I saw a link to Pearson,
A link?
yeah,
Oh, no, the Pearson one, I have no control, but someone gave me a PDF version,
oh, yeah.
so I can upload the PDF version. I mean, I don't think they will allow me to do that because it's 1,000 pages long. I can email it to you.
Oh.
Send me an email,
Yeah, I
so I can
did
just reply.
the one for the office hours is the same email. Yeah, okay,
Yeah.
thank you.
Yes. Well, have a good weekend. Start doing the homework, showing all the work.
Can I resubmit the one that I?
No, the one you already did, you cannot. But the future ones,
But, I mean, you could show where, but I submitted it.